All right. Thanks everyone. My name is Minji Chen. I'm a assistant professor of electrical and computer engineering at Princeton University. Today we're running the MagNet Challenge webinar series 3, and we'll be focusing on machine learning methods for core loss modeling of power magnetics. I just want to give you guys a quick update of the status of the competition. Right now we have 39 teams registered from 19 countries. And again, as we said, we'll try to host as many teams as possible. So if you know your friends or any of your colleagues are interested in participating, we're still open to registration. We also have posted many tools and codes available in our GitHub. So feel free to check and you'll find any problems. Or if you have your own tools that you want to share with the community, feel free to let us know. Or you can even just fork it from the GitHub repository and we can run it in a typical open source way. So we also want to remind that there's one 2-page concept paper due in about 1 month, June 15th. So the purpose of the concept paper is not trying to filter teams, but trying to make sure everyone understands the rule. So when you're drafting the concept paper, you probably will raise questions about how about the competition, the rules of the competition. Feel free to send us the email, and we will hope to clarify everyone's question before we enter into the real competition stage. So before we start the presentation, I want to actually open the floor. And does anyone have any general question about the competition? Okay, if not, you're welcome to post your question in GitHub, and we regularly check GitHub and we'll give you answers if there's any question. So without too much question, then I'll pass the stage to Haoran Li, who will give us a presentation on machine learning based methods for power magnetics core loss modeling. And again, let's run this more or less like a discussion. So if you have any questions at any time, feel free to unmute yourself and ask questions. Okay, Haoran.
Okay, thanks. Thanks, Miji, for introducing the webinar. So can you see my screen now? Yes. So yes. So everyone, welcome to this webinar. And this webinar is one of the series webinar for the 2023 MagNet Challenge. And this is the third one, which will be focused on the machine learning method for the power magnetic modeling. Sorry. So as a quick reminder of our background for this challenge, as we know that power magnetics such as the inductors and the transformers are critical in the power electronic system. But on the other hand, they also typically occupy the largest volume and introduce significant power loss, which limiting the system optimization and make them the bottleneck of the system. So to properly design the power magnetic components, we need a precise model. Otherwise, this could potentially lead to time-consuming iterations back and forth between design and test, or lead to a large design margin to make sure this works properly under any conditions. That's why we need that's the motivation that we need a precise model for the behavior of power magnetics. However, modeling the behavior of the power magnetics, especially the hysteresis loop and the core loss, is really challenging. The behavior of the power magnetics can be impacted by various factors such as the waveform shapes, the frequency, the temperature, and DC bias. And at different operating conditions, the behavior of the power magnetics, especially in this case, the core loss, will be different, which makes the modeling to get a precise model for the core loss is really difficult. So far, most of the power modeling for the core loss is using the analytical model or equation-based model. So from decades or even hundreds of years ago, there's limit equations where they use it's used 3 parameters to model the core loss. However, it's known throughout that the limit equation only works for sinusoidal waveform. And then there comes the improved generalized Stamets equation, which is known as the IGSE, which is one of the state-of-the-art equation-based model, where there are still 3 parameters the same as the Stamets equation, but in this way it can work for arbitrary waveforms and get a better accuracy. And furthermore, there comes the I squared GSE, where you use more parameters. But in any case, most of these equation-based models, they are hard to cover all of the influencing factors into a single equation, such as the temperature, DC bias, all of these effects. And besides that, on the other hand, now we are trying to explore the neural network methods to see if this is a better opportunity to do the colors modeling. The neural network models typically contains hundreds or even thousands of parameters, which offers much more capability of learning the patterns and the principles of the colors. And with neural network models, one can input the shapes of the waveforms together with operating conditions such as the frequency, DC bias, temperature, and to use the neural network to predict the colors. As we know that the neural network has been extremely effective in modeling this kind of multivariable nonlinear problems. Now, as you know, that the neural network is a very powerful tools, and for different problem settings, will actually lead to different input or output settings, and which means we can use different types of neural network structures. And in this webinar, we hope to cover three types of the neural network models. The first one is the scalar, where the input is a scalar, such as the frequency, flux density, amplitude, temperature, DC bias. And then the output will also be a scalar, which will be the colors. And secondly, there could be second scalar model, where the input will be directly the waveforms of the excitation. And then we predict the colors under this specific type of excitation waveforms. And thirdly, there could also be the second-to-sequence model, where we model the relationship between the excitation waveforms and the response waveforms. In this case, for example, we use the beach loop as an example. We input the flux density waveforms to predict the field strength waveforms. So before we go into the detailed examples, here's a few things to point out to the goal. Firstly, the goal of these examples is to highlight the typical workflow of the neural network modeling for parametrics. It's not necessarily being a comprehensive one. And the data set and the algorithm in this tutorial is not exactly completely the same as the one for challenge. And thirdly, all of the examples in this tutorial is based on PyTorch framework, but of course, all the teams are welcome to use any other machine learning framework that they are familiar with, such as TensorFlow or scikit learning. And finally, all of the tutorials mentioned in this webinar is already available in GitHub, and you can check it out and to run it by yourself to see how it works. So firstly, let's take a quick look at the typical workflow of the network training. So the first one, before training, you need to do some pre-processing of the dataset as needed. Sometimes, because in the original dataset we provided in this challenge, it contains the waveforms of the B and H, and then the value of the frequency, temperature, and the calculated colors. But this may not exactly fit the need that you want for your network settings. So you need to do some necessary pre-processing before you feed the dataset into your neural network. And secondly, after the dataset is prepared, you will randomly split the dataset into training set, validation set, and test set. For the training set, is used to, of course, to train the neural network to tune the parameters. And then for the validation set, it's used to select to validate the performance of the neural network, and then to select the best one. And finally, you can evaluate the performance on the test set so that you can know if there is some data that is never seen by the neural network, what's the performance on these new data points. And based on this, there's a technical k-fold validation is typically recommended. This can help to improve the generalization capability of the neural network. And thirdly, after we have the data set ready, we can now get to define the network structure. So the network structure could be in many cases, such as we already mentioned, could be different types of inputs, such as the sequence input or scalar input. But in the end, we want to emphasize that we hope our teams can tag the neural network model into a standard functions, so that in the end, when we evaluate your models, we can have a standard input and output format, so that we can evaluate in a more fair way. And fourthly, after defining the neural network structure, we can now define the training iterations. And within the training iteration, there are several things you need to pay attention to. The first one is like the loss function, which is important to calculate the loss during the training. And secondly, the learning rate and its scheduler, and thirdly, the optimizer. And finally, with all of these settings, you can now train your neural network, evaluate the results, and then iterate these iterations and to fine-tune your network model. Now, more detailedly, let's firstly take a look at the pre-processing of the dataset. So for the pre-processing dataset, one of the most frequently asked questions about our dataset is like whether there will be tags for the waveform shapes. So as of now, we didn't provide tags for waveform shapes in our dataset. So the teams in this challenge are expected to develop models for arbitrary waveforms. And by arbitrary, in this case, we mean sinusoidal, triangular, and trapezoidal, these three types of waveforms. And the model is expected to work for all of these three types of waveforms at least. And based on this, you can either may or may not develop your own classification algorithm to integrate into your model if needed. Secondly, for different fields of data that we provide in the dataset, such as the flux density, frequency, temperature, field strength, and power loss, they have significantly different magnitude. So it's really it's typically preferable to do the data normalization so that they can be normalized into the same range. And also maybe you hope to do some data transformation, such as for the power loss, you may want to calculate the logarithm for it because it could vary in different magnitude. And by doing the by calculating the logarithm value, you can greatly improve your numerical stability. And thirdly, as we mentioned, that the waveforms in the dataset we provided are the single cycle B and H waveforms, and they have the same starting phase. But by doing that, to further improve the generalization capability of this waveform prediction, you may want to assign random phases and the reasonable white noise to it, so that we can help to improve the performance when the neural network is predicting based on the waveforms that they never know. So all of these pre-processing tools, some of these have already been developed in the MATLAB codes, and we also uploaded, as Professor Chen just mentioned, in the GitHub repository, so you can check it out if there is anything that helpful with you. Now let's take into some details examples. The first one is the feed-forward neural network. So here is the brief overview of the network models. You can think about it as a neural network version of the statement equation, where the input will be scalars, including the frequency, flux density, amplitude, temperature, diffusion ratios, etc. And output will also be a scalar, which is the predicted colors. And by doing this, you can calculate the colors based on the predictive values of these scalars. And the advantages of this one, of course, is a very straightforward to implement, because the feed-forward neural network is quite fully connected neural network is quite the most simple neural network structures, and it's very easy to train. And but the disadvantages of this one is, like, as you can see, it will lose the information of the waveform shapes, because in this case, the waveform shape you have to describe with some scalar inputs and may lose some details. Now let's take a look at the detailed code. So the codes have been available in this Jupyter notebook and have been uploaded in the GitHub. You can take a look, and also with the dataset you can train it by yourself. So firstly, to do this network training, the first step is to import the necessary packages. In this case, we are doing the training based on the PyTorch frameworks. But as I mentioned, you can use whatever framework you want, such as TensorFlow or scikit-learn. And on the other hand, we also want to mention that as we know that there is like almost infinite packages, all kinds of modules available in Python. But in the end, we don't want to have this too many all kinds of packages in there. But of course, during your modeling, you need to use some tools that may not be directly coded by yourself, that is offered by a third party. In this case, we hope that every module that you use is open source, so that when the judge committees evaluate your code, we can run the codes to reproduce whatever result you have based on these open source packages. And with here, we import all of the necessary packages, and then we can define the neural network structures. The first model, as we mentioned, is the feed-forward neural network, and you can refer to the PyTorch document for more details. So here, Firstly, we define the structures as the as a stacks or multiple layers. So each layer is a linear, which means the fully connected layers, and followed by a ReLU function, which is the activation functions of this neural network. And in this case, we have stacked the 3 hidden layers together, and each of the hidden states contains different number of hidden neurons. And in practical, you may want to set the number of layers and the number of neurons in each layer as variables, so that you can do automated search and organization for this number of layers and neurons. And then there's the forward propagation function of this one. It's very easy. You just pass through all of these hidden layers and also the activation functions. And finally, the output will be a single number, which is the colors in this case. And here we also coded for a program for a simple function to count how many learnable variables, learnable parameters that contains neural network, so that you can get an idea of how large your network is. In the end, we don't hope you get a very extremely large network, or even as large as a lookup table, which doesn't really make sense for this colors modeling. In the end, you hope to balance the network size and the accuracy. Now, with the network structure defined, the second part is to load the dataset. In this case, in these specific tutorials, we are training the neural network based on the small dataset that contains only the triangular waveforms. And again, in the dataset that we provided for the challenge, the types of waveform shape is not provided as tags. Indeed, you can either generate your own classification algorithm, or you can just ignore the type of waveform and generate the model for arbitrary waveforms. And in this case, we have the datasets which contain the frequency, the flux density of the amplitude of flux density, and the duty ratio is calculated based on the waveforms in this case, and finally the power loss. And then you may want to do some pre-processing before feeding it to the network, as we mentioned. In this case here, as an example, we do the calculated logarithm values, because as inspired by the stem equation, there could potentially and approximately exponential relationship between the colors and the frequency flux density. And we found that it's actually helpful to do this logarithm, calculate the logarithm value before feeding it to the neural network. And then based on this, we can do some reshaping and format of this one, and finally change the dataset into the tensor that the PyTorch frameworks actually takes this tensor as dataset. And thirdly, now we program the algorithm, the iteration for the training and testing. The first part is about the reproducibility, where you set the random seed and all of these default settings, so that when you train the neural network, you can make sure that every time you train and test, the result is reproducible. Secondly, there are some hyperparameters, such as the number of epochs, which means how many epochs you want to train your neural network. Typically, the longer you train, the better it gets. But you also need to actively monitor the training process to make sure there is no overfitting happens. And secondly, there's the batch size, which means how many batches you want to train at the same time. This is also a very important hyperparameters that you may want to optimize it so that you can eventually get a good model performance. And thirdly, here are some parameters about the learning rate. So here, the learning rate, you can firstly set the initial learning rate, and then there are also the schedulers. So here we choose the exponential decay learning rate, where we set the exponential decay ratio and also how fast it will decay. And thirdly, you can set the device you train this neural network. So here we use the GPU we use the CUDA for the GPU. And as a recommendation, we recommend all the participants to probably try out the Colab, which offers very simple and easy setup for the GPU devices. And you can easily get access to the GPU without much knowledge of the GPU programming. And with all of these settings, now we get to the main part, where firstly we load the dataset as we already programmed. And after load the dataset, we can now split the dataset into whatever we want. So as we mentioned, we need the training set, the validation set, and finally the test set. Here we use 60% of the entire dataset as the training part, 20% and 20% for the validation and testing. And these data sets will be split and to pack into this data set loader as required by the PyTorch framework. Now, as the data set ready here, then we get into the network. We generate the network as we defined at the very beginning, where it contains the 3 layers, hidden neural network, hidden layers. And then we can define the loss function for the backpropagation. Here we use the most simple one, most straightforward one, the mean squared error. And there is also many other options for the loss function that you can try it out by yourself. And secondly, there's the optimizer. So there's also many options for the optimizer. Here we choose one of the most commonly used, the Adam optimizer. You can also choose one of your own preferred, such as the SGD optimizer. And all of these settings will affect the performance of the neural network training. Now, with all of these settings, now we can program the actual training and validation iteration of the network. So based on the number of epochs you want to train, for each epoch, firstly, you will train for the network. Based on this, you firstly reset your loss and set your network into the training mode, and to calculate the actual learning rate at the moment. And then we firstly do the forward propagation, where you use the input and the output in the data load in the training data set to calculate the output, to calculate the predicted output based on the neural network. And then we can calculate the error, which means the loss function between the output and the actual core loss that you already know in your database. And based on this loss, you can then do the backpropagation, which will be automatically calculated by the neural network engine. And based on the backpropagation results, now you update all of your parameters in your neural network, and that this finished one of the iterations of the training. Now, after one iteration of the training, the parameters in the neural network is updated, and then you can try to compute the loss on the validation set to see how much it improved. The validation set is quite the same, where you use the inputs to input in the validation data set to calculate the output, and then calculate the loss between the output and the expected output. But in this case, we no longer do the backpropagation because this is only for evaluation on the validation set. The backpropagation only happens in the training set. And finally, you can code it for you can do some coding to monitor the training process to see how much loss you're getting, and then you can see the loss is gradually dropped, and eventually the model reached to the converge where there's a reasonably low loss. And finally, you can save your neural network and do the evaluations. For the evaluations, is the same as the validation set, but it's now doing on the test set. The same, you are calculating the output based on the data in your test data set. And to make it more interpretable, here we want to calculate some metrics of the predicting results, such as the relative error or the average error, RMS error. And here, before doing that, since as you remember that we calculate the core loss in the logarithm value, so in order to make sure the calculation result is correct, we need to converge back to the actual value by taking the exponential. And based on the predicted result and the actual measure result in the dataset, you can now calculate the relative error or whatever metrics you want to report as the performance of the neural network. And this contains the entire workflow of the neural network training, from training to validation to testing. And here, as example, due to the time limit, we won't run this. This is what I run in advance. So here we can see this is the output contains how many data you contain in your data set, how many parameters you contain in your neural network. And here is the monitor the process of the training, where during the training you can monitor your losses going down and down, and finally reach a converge. And finally, you can get the evaluation on your testing result, where in this case, the relative error is about 3%, and the maximum error is about 15%. Now let's go back to this to the slides. So as in the example, we have already showed the simple evaluation result. And more generally, here
maybe we can pause for a question, I guess.
Yeah, sure.
Are there any question?
Yes, this is Daniel here. I was curious how you decided on 3 hidden layers.
Yes, so the number of layers and the number of neurons in each layers is actually one of the hyperparameters that you want to optimize. In this case, in the end, we're gonna recommend one tool called Optuna, which is an automated tool to search for the optimal combination of these hyperparameters.
Right. So I guess the answer is we don't know. That's why we sort of, one of the motivation we are very excited about this competition is that we sort of figure out a way which barely work, but we don't know how far what we have is compared to like the optimal. Like we don't know where's the optimal, and we look forward to see innovative structures that really can capture the complexity of core loss. Any other question? No, then Hara, maybe go ahead.
Yeah, sure. Yeah, just as we said, so here we show a few examples of our previous result on this feedforward-based neural network. So here we can see that in this specific case, we test with the triangular waveforms with different duty ratios. And as we can see, for different duty ratios, the neural network is capable of predicting pretty accurately. And here we also show the difference between the relationship between the number of neurons in each layers and the absolute and the average relative error of the core loss predictions. So as you can see here, as we increase the number of neurons, the total number of parameters contained in the neural network is increased, and at the same time, the relative error of the predicted core loss also drops. So here we can see that the network performance is closely related to the network size. And here we fix the number of layers to be 3, and just as you asked, so as we can also increase the number of layers to make the neural network even deeper, which potentially results in a better performance. So to balance the size of the neural network and the accuracy is actually one of the most important things during your network training. Now the second example is based on the LSTM neural network, which stands for the long short-term memory, which is it's a special types of the recurrent neural network. For the recurrent neural network, is based on the recurrent connections. It can process the sequential input. For example, in this case, we designed this neural network to take the sequence input, which is the waveforms of the excitations, and in this case, is the waveforms of flux density. And the output is still the scalar, which is the predicted core loss. And you can treat it as the neural network version of the IGSE, where the input will be waveforms, output will be a scalar. And the advantages of this one is now based on the recurrent neural network. In this special case, the LSTM neural network, it will naturally take the waveform shapes into considerations because the input will be sequenced, and it doesn't matter which type of the waveforms you have. Doesn't matter if it's a sinusoidal, triangular, trapezoidal. It's all treated as a sequence and as the sequence input of the neural network. And on the other hand, it's potentially difficult to incorporate other conditions, such as the temperature or the frequency, into this neural network, because in the end, we need to combine the output of this LSTM stage and feed it back to a feedforward neural network so that we can, in the end, generate a single number, which is the core loss. Let's look into the code of this one. The second notebook is also available in the GitHub. You can check it out by yourself. So here, as before, we also import the packages in the same as the first one. And the difference here is the neural network structures. Here you can check out the PyTorch document for the LSTM to see how the LSTM neural network works. The LSTM neural network is very good for doing this sequence input modeling. And here, in this case, we firstly define the LSTM neural network, which contains one LSTM layers. For each layers, it contains 18 units. And this could also be one of the potential hyperparameters to be optimized. You may have multiple numbers of layers and multiple different numbers of neurons in each layers. But of course, this will change the size of the neural network.
All right. Wait a minute. There's a question. Maybe let's just answer the question now.
Oh, yes.
Please go ahead. Are you?
Okay, thank you. Sorry. I have a question in the part of the feed-forward neural network. So you use the Optina to determine the optimal number of hidden layer, yes?
Yes.
To obtain the best result. But what about the number of neuron?
Both of them can be optimized.
Ah, okay.
Yes.
I have a second question. It is possible to have in output a sequence too, like LSTM, or no? With using the FNN.
Sorry, what's the question?
My question is, it is possible to have in output a sequence too? Sequence.
Yes, theoretically it's possible to have a sequence output with the feed-forward neural network, but actually we don't really hope for that, because the neural network, as you can see here, is typically it's a fully, for the feed-forward neural network is also known as the fully connected layers. So in the end, usually it's like you have a single or a few outputs. If you want to have a sequence here, for example, you have a long sequence of output here, which means you will have a huge number of output neurons in the last layers, which could end up in a very huge neural network, which is not what we desired. And also on the other hand, the feed-forward neural network naturally doesn't really design for these kind of sequence-to-sequence problems, where the recurrent neural networks such as the LSTM has been proved to be much more effective in dealing with sequence.
But my comment will be, you are welcome to try anything you think makes sense. So if you want to produce a sequence within the function, and in the end combine the sequences and calculate the BH loop, get a core loss, feel free to do that. So we don't need to know what you do within your function, as long as your final output is a single scalar.
Okay, thank you.
Yep.
Right. Yeah, so just as a follow-up, so as we mentioned that the number of layers and the number of neurons in each layers together with other hyperparameters that we just mentioned, for example, here the batch size and also the learning rates and how it's decayed, all of these hyperparameters could be optimized. And you can either do this by manually trial and error, which is of course super time consuming, or you can use some tools such as the Optuna, which is very helpful in doing this automatic hyperparameter optimizations. So in the end, you can based on your expectations, you can get a reasonable combination of these hyperparameters, like how many layers you have, how many neurons in each layer you have, all of these hyperparameter settings. And let's go back to the LSTM here. As we said, firstly, we define the LSTM layers, which contains 1 layers and 18 units in each layers. And then it's followed by a feed-forward neural network, which will process the output of the LSTM and then finally convert it into a single number, which is the core loss in this case. Now, for the forward propagation of this neural network, firstly, you pass this X. In this case, X is no longer a scalar, but a sequence. The sequence will be passed through this LSTM, and then we get the LSTM output, which is only the last time step. Which we only care about the last time step because we need to make sure the LSTM already processed the entire sequence, and then we get the last time step output, and then we take the output, feed it into the feed-forward neural network to generate the single output, which is the core loss in this case. And everything else in this case is the same, except the data set. So in this case, in the data set, because now it's the input is sequence. So here we use the sequence, which is the waveform of the flux density in this case, to feed as the new input of the neural network. And output is still the power loss, where we still, as previous, we take the logarithm of this power loss, and we convert this into the tensor variables and feed it to the PyTorch framework. And in the following part, the training setting is almost the same. Firstly, program for the reproducibility and finding the hyperparameters. And of course, since the neural network structure is already completely different, it's typically that you have different hyperparameters for this case, for different cases. And then the rest part is the same. You split the data into training set and the validation set and test set, and you train the neural network doing the for the propagation, calculate the loss during the back propagation, optimize to update all of the parameters in the neural network. And after that, you can calculate the validation loss, and finally the evaluation on the test set. And here we show some examples of the training result that I run previously. Similarly, as we can see here, we have the number of data points in the data set, but now it will be a 2D array, where the second dimension is the length of the sequence. In this case, I selected at 1000, and output is a single number of the colors. And now, as we're using the LSTM, which is a more complicated neural network, the number of parameters will be much significantly larger than the before neural network. And now, as the training goes on, you can still see the loss on the training set and the validation set going down and finally approximately converged. And the evaluation result will be, in this case, 5% relative error and 9% RMS error. But you can see the maximum error is actually pretty bad in this case. And that's why we want to emphasize that in the end, at the moment, we decide that the evaluation result will be, the evaluation will be based on the 95th percentile, which means you need to get a good prediction for most of the data points that contains in the test set, so that we can see the neural network has a good performance.
All right. I noticed that you are using JSON format in PyTorch. So the student teams will have to convert the CSV we provided to JSON, right?
Yes, this is only this is just an option. You can use whatever data format you want. So currently in the data set, we have the CSV in all of the data set that we're providing in our database. And from the CSV files into the Python, you can choose whatever you want, such as the NumPy files or using JSON, or directly read the CSV.
Okay.
Yes.
Okay.
Let's go back to the slides. So as we mentioned that for the LSTM neural network, one of the advantages is that it's no longer differentiate the types of the waveforms. As long as we provide the sequence input, it will be able to predict the colors for the given input waveforms. Here are some examples of our previous results that we tested, that we trained the neural network based on the mixed data set of the sinusoidal, trapezoidal, triangular together. Here we can see for this one, all of the three types of waveforms got a reasonably accurate prediction for the colors within this using this single neural network, which means the LSTM can work for mixed waveforms with just a single one, because it's taking the sequence as input. Now the third example is the transformer neural network, which you may heard that recently the ChatGPT is very famous, and is the fundamental basis of this one is also the transformer. So the transformer is also used to deal with the sequence input, and in this case we developed this encoder projector decoder architecture for the bit loop modeling, where the input will be a sequence, which is the waveform excitations. In this case, we define as the flux density, and output will be the waveforms of the response, which will be in this case the field strength, the H. And at the same time, we will also take some scalar inputs such as the frequency and temperature, and DC bias is not included in this challenge this time. So the advantages of this encoder projected decoder architecture is that it can naturally combine the sequence input and the scalar input into a single integrated framework, so that we can predict the waveforms, predict the behavior of the power magnetics under different shapes of the excited waveforms, and also under different operating conditions, such as the frequency and temperature. And the disadvantage is that in these specific examples we have, as you will see, that the information of the colors is not directly taken into considerations, because in this case we are predicting based on training and predicting based on the H waveform to predict the bit loop, and the bit loop, from the bit loop to the colors, there is usually a gap between this. Now let's look into the details of the code. So this is the third notebook for the tutorials. It's also available in the GitHub. So in this case, the package is the same. The network structure is much more complicated in this case, and I would recommend you to refer to the document of the transformer of the provided by the PyTorch to see how it's actually programmed. So here we quickly go through it. So firstly, you will define the encoder, which is you will define the encoder, which is you can see here. So here for the encoder, you firstly have the input layer to map the encoder into the sequence. And for each sequence, you have added up with the positional encodings so that we know the temporal information within this sequence. And then go through a relatively complicated neural network. And this is essentially the original transformer neural network that they proposed in the well-known paper that attention is all you need, that paper. And based on that, we insert one of the projector in the middle where we take the output of the encoder part and mix it and then modify the results of the encoder part with the extra scalar input, such as the temperature and the frequency in this case, and then feed the modified hidden state into the decoder part to generate the output. And here you can, if you're interested, you can take a look at the detailed code, which is quite complicated compared to the feedforward neural network and the LSTM neural network. But in the end, if you take a quick look of the results, as you can see, based on this projected decoder, we are capable of predicting the bit loop with reasonable accuracy. As you can see, as the training proceeds, the accuracy of the bit loop prediction increases, and in the end, get a pretty good match between the measured bit loop and the predicted bit loops. And if we want to evaluate the performance of this neural network, we can firstly calculate the relative error of the sequence, because this neural network is essentially trained based on the match between the predicted H waveform and measured H waveforms. And also, and based on the predicted bit loop, we can then calculate the core loss based on the integral, which is the area of the bit loop, and so that we can get the evaluation of the core loss. And as we mentioned, that currently in this tutorial, as you may find in this notebook, the training is purely based on the sequence matching, where the loss function is defined as the predicted H waveforms and the measured H waveforms. And the core loss, the information of the core loss is currently not implicitly taken into considerations. But as you may know, that the core loss is very sensitive to the phase mismatch between the B and H waveforms, and a small phase mismatch could lead to a huge error in the core loss. And that's something that you can potentially improve based on this example. And in the end, here are some tips for the neural network trainings. The first one, as we already discussed, that you may want to properly balance the trade-off between the model size and the model performance. As we said, you don't really want to have a extremely large neural network. And in the end, the size of the model is also one of the evaluation metrics that we will take into considerations during the final evaluations. And to do that, you may want to use some existing tools such as Optuna, as we mentioned, to optimize the hyperparameters, such as the number of layers and number of neurons, to get a reasonably large neural network while achieving a very satisfactory accuracy. Secondly, for different magnetic materials, currently we provide 10 materials in our database. For different magnetic materials, they may have different behaviors, which potentially lead to different difficulties to model it. Some might be easy, some might be difficult. And based on this, you may want to comprehensively train and test your model based on all of these 10 materials and get a feeling of how much number of neurons, number of layers you need. And then when the testing materials coming out, you can quickly fine-tune and adjust your model to fit the new materials.
One comment here. So we don't restrict you to use one model for model 10 material. You can customize your model for each of the material based on what you see, or you can have a pre-classification function within your model to first classify the material and select the right model for the right material. So what we need in the end is that for the 3 additional material that we're going to offer in November, you have 1 month to develop the model. And what we need is really more of a working flow so that you can quickly find the right model structure for the right material. So the short summary is that you don't have to use one model to fit 10 material. What we need is that we need you to be able to quickly find the right model for the right material. So I hope this clarifies the question. But of course, if you find one model that fits every material, just like Steinmetz equation, it's like you use one model to fit all the material. We welcome that, but we have to finally evaluate whether this model is applicable, accurate, with smaller size and very few number of parameters. So I guess this is open for discussion. The bottom line is that you don't have to use one model to fit all the material.
Exactly. And the third part, as we also already mentioned, that you need to take extremely care of the overfittings, because the neural network is very easily to suffer from the overfitting issues if you don't have the proper settings of your for your neural network structures or your number of data points in your data set. So to ensure the good generalization capability, you need to keep an eye on the training results during the training proceeds. So, and also take a look of the metrics and also especially the distribution or the predicted error to see if there is any overfitting happens. And finally, there also, as you may know, that there's a tons of tricks to set the the loss function and the learning rates to improve the neural network performance. And this is important and it's very critical to the network performance. But on the other hand, we still hope to put more emphasis on the innovations on the neural network structure and algorithm rather than these kind of tricks, so that we can, in the end, we hope that you can have both innovative structures and as well as a good performance based on your own tricks of this network training. So that's the tutorials. You can find all of the codes and tutorials in this GitHub. And thanks for your interest.
Okay, Hara, maybe you can pull out our GitHub and explain how do they locate the tutorials and files.
Yep. So currently this is our magnetic GitHub. So maybe you want to also I will also upload this to our challenge. Yeah, this is a repo for our magnetic challenge. So in the end, we will also upload this into this one. So this folder currently is located into the main repo in the tutorials. And here is the transformer models, where it contains the notebook for the training and the testing. And here we also show the examples of the outputs here. And for training this one, you can use the datasets contained in this file. And in this one, because it's a tutorial, we want to make it faster and easier. We only contain central waveforms in this one. And here is also the LSTM result examples of the network training and testing. And here, as we showed, the feed-forward neural network one is contained in here. I will upload this one into the main repo as well. This contains the feed-forward neural network and the LSTM training for both of them. And the corresponding dataset is contained in the dataset folder.
So it looks like so some of the code are in the MagNet repository. So we'll move everything into the MagNet challenge repository.
Right. I will move everything into here to make them synchronized.
Great. Yeah, I think that's pretty much all we have. Any question? We'll open the floor for questions.
Hi, Haoran. Thank you for the presentation. I have a question about the accuracy for these models. Has any of the models already meet the 95% error requirement? I'm wondering how much improvement, how much room for the improvement we have.
So for this one, you can take this one as a reference. Here we calculate this transformer. This is based on this transformer model where we calculate we are actually doing the Bayes loop prediction, and then based on Bayes loop prediction, we calculate the colors to get the predicted colors. So here we can see it's approximately Gaussian distribution with the standard deviation about 7%. So this you can get a brief feeling of the 95 percentile is like let's say 15%, something like that. And you can treat this as approximately as a baseline. And so then you can see if you can get a better results compared to this one.
So I guess, Helen, to answer your question, I think for accuracy, probably this is almost what you can get, but you can probably make the model bigger to get more accurate. But we think there are huge room to improve for the model size. So right now, our model, we didn't do exhaustive search, and we think there are a lot of ways to make the model much more compact. So I would say, in terms of accuracy, maybe single digit error for 95% stage error is probably what we end up targeting. But in terms of model size, we don't know how much room. We think there are a lot of room. We don't know.
Okay.
Yeah.
What is the model size right now you have? Is it a file size or you mean parameters, numbers?
Parameters. So we end up, we'll be using the number parameters to compare either equation-based model or neural network model. Right now, for the sequence to sequence, we have like 5,000 or 50,000.
Yes, so to get a brief feelings for this kind of beautiful neural network, you can typically have a few hundred to a few thousand, and similarly for the STM. And for more complicated models, such as the transformer model, you have currently this one have like a 28,000 parameters.
Right. So it's huge. Transformer model like 28,000. But if you go with the equation-based model, maybe you just need 10 parameter or 20 parameters. So there are a lot of room to compress the model. And we didn't use the advanced techniques so-called like neural network pruning. I think that there are ways that you can drop the weights, which are close to zero. So there are a lot of neural network compression techniques that maybe some of the team want to try. Like we didn't try any of those.
Okay, thank you.
Any other question?
I don't know something.
Looks like we are good and we're close to 1 hour limit. So I guess so we'll have one more webinar next week, which we will be talking about data complexity and data quality and how much error we think we have between our data and the real measurements. And also the difference between our data and manufacturer reported data. So we just want to make sure like every team understand, well, this is the competition, but on the end, it's only a competition. There's also always a gap between games and real world scenarios. And regarding machine learning, I guess the final recommendation we want to give is that don't spend too much time like fine tuning or trying to improve the error by like 0.1%. So because if you switch from one material to the other material, maybe the tricks doesn't matter. So focus on the important concepts, focusing on creating new understanding about magnetics, probably will lead the method for a long way, because we want the method we develop to be applicable to a wide range of materials. Yeah, so that's pretty much all we have to say for this week. So if you have any questions, feel free to stay and we're happy to chat. You can turn on the camera and we can chat. Otherwise, we'll conclude this webinar and we'll see you next week.
No, but I'm gonna